Right, so welcome back to part 2 of the cloud computing and big data course today, which is about the practical lecture, really connecting lots of theoretical elements we had in lecture 2 about machine learning in general. And then also lecture 3, which was really looking underneath what Spark has to offer. And we really try in this machine learning lecture today, in this practical lecture, to shed some light on how that really works in conjunction together, and also how you could derive, let's say, a kind of machine learning overview in a practical fashion in order to go to new problems that you have not really seen before. The logistic regression example here now is known by everybody of you. So you see that that should essentially work. And here in this practical lecture 3.1, you see also the connection then I try to do here always with running jobs. And in the second part, we will come to, of course, much more details now about the modeling. And this is a part 2, because part 1 was largely setting up the cluster, basically having the data explored a little bit. We have seen that different classes which not really fit our binary thought. So we have to work on this a little bit, but this is just natural. So wherever you come, you rarely throw data just to a machine learning problem. Usually you have a lot of work on feature selection, feature engineering, data preparation to do in order to fit a certain machine learning algorithm. So this will be now the second part. We will look much more in the machine learning algorithms, the hypothesis we kind of established of saying it should be logistic regression. So we have to evaluate it and we have to see how it really learns. So what means learning here? We said it's iteratively, but how can we see that? So, and then with this, we also will go to the advanced notion of pipelines in Apache Spark and in data science in general. So we said and left basically on a sad notice and said linear classification with a simple perceptron, yes, just using the sign function would be probably not strong enough, especially as we know that it has some limitations in the perceptron learning algorithm. We know that it must be linearly separable. So here you have a much more stronger function, logistic regression. Of course, it's binary, still a binary classification problem, but we put that out of all of our tool set, right? So we have a large hypothesis set, capital H, and every one of those, logistic regression is H1, H2 might be support vector machine, H3 might be random forests. So you pick that out of your tool set according to your kind of skills you have with these algorithms, and then apply it with your skill set to a common problem, right? So this is a very nice set. You have a tool set, which is Apache Spark, delivering you the logistic regression tools. And then now your skill set says, okay, I know how to handle it. I know machine learning. And we know we have a certain function. And this model function is down there. It's 1 over 1 plus e to the minus t. But it's a very, let's say, logistic function, very established. It's not that you have to redefine this all the time. And anytime, basically, I do a learning iteration, we basically need to change the weights, right? The red entities. And with this, I also change a little bit automatically the hypothesis. That's why it's H, also in red. So we put the signal not anymore through the sign function, but through a logistic function, which says at every value, so to speak, that comes out of this, you see that here nicely, will somehow go between 0 and 1, because also what this figure maybe illustrates a little bit wrongly is it will never touch 1, it will never touch 0. It actually is, converging to this, but still, no matter how far you go to the right and left, usually it squashes the values to between somewhere 0 and 1. It shows you also that machine learning is not totally accurate, right? It gives a tendon kind of idea. It goes more to the 1 or it goes more to the 0. And this, of course, reflects the nature that data sometimes is not like black and white, that there is some certain part of it, maybe in the language, that could be a violation, but maybe it's not completely a violation in our example. And this is just a typical practical problem you will encounter when doing machine learning. Right, so having picked that, we have seen that when I want to pick this, I have 5 classes. So how the heck should I do this with binary classification I have on the right-hand side, where I know my data should be fail and pass. And we said this is the only thing that interests us in this application example. So we can play around with this. And you've seen some of the elements that just, are there. It shows you how many classes we really have, 5 classes, and you see also the count of those class representatives from the data samples. So the majority is really on PAAS. So with this, we have lots of data in different classes, but we want to join them. And I think all of you have done this now in the assignment a little bit and have seen this in the lecture, that there's not much news to you how to do this. You have seen here the output of the Jupyter having a nice illustration, showing you a little bit also that the data is quite, a little bit biased towards this PAAS direction, but we also merge several data sets to be on this, what we want to do. But in the end, it's a toy problem, so to speak. It's not that complex. So in this sense, we still can see that the machine learning machinery we will create out here is, let's say, very much okay. The other thing we see is that visualization really helps understanding the data. On the right-hand side, you see that much more in an interesting fashion with infographics today, which are extremely often used with data analytics. But this is really helpful also if you not have this fancy ones from the infographics. However, of course, this one that you see on the left could fuel one of the small parts of an infographic, depending on your application problem. For instance, if you have to show your CEO something about the food inspection results and the data we had previously, maybe this could be something to integrate in an infographic. So visualization is important, but we want to go to modeling. And we said in order to model this as a binary classification problem, as we said, we really want to have, let's say, our labels a bit feature engineered if you want, right? So the kind of feature is not really a feature because it's our output label. So it's a bit more saying it's data preparation. The feature would be more the violations and so on and the words on that. Here we're talking about the outcome Y, the class. So here we wouldn't say necessarily feature engineering. Rather, what we want to do is data preparation to fit it to a binary classification problem. And you see that a little bit here on the right-hand side, we put, for class 0 and 1, we put fail, of course, very clearly, but we also include in the PAAS with some conditions. And basically the rest of the data we just filter out. And this is what basically you see on this couple of lines of Jupyter. So with this, we have now a very clear aspect. So now we are ready for binary classification problems because we have still, of course, in a way, the nature that the PAAS is kind of 2 classes, but it's modeled here as 1. And this is all we need. Of course, we have to take as machine learners practically into account that there is some problem with it. So when you do this now, and you have done this already, maybe in your assignment or so, and we will look back to the cloud, how it is doing this. We basically select an application problem. We include the logistic regression for it. That's what we wanted to do. And we said, okay, now we have essentially this picked, but we don't know exactly how it works. So in our code, we have this logistic regression where there's maximum iteration and things like that with parameters. And I come to this in a moment. But essentially, we're saying now with the data on the right-hand side, having 2 classes really from the training data we can learn from, that is now how we can start. We have the model function. It's a logistic function. And basically, then we know directly how to work with it. However, for learning, we need more elements. And I will come to this in a moment. Before we go there, in the training process, let us just review what the cloud has done in the break. I was just re-executing it. And again, it's sometimes mysterious errors. But you see here, I just executed a couple of minutes ago here in the break. We basically had the same elements before we took the data. The beautiful thing here is you see always the jobs that are running, right? So this is now reflecting the tasks which were taken to this yarn scheduler and really put out of the cluster, and it's just one stage, so it comes back. It's a very simple command if you see inspections take, but it shows you that things are not anymore of some login node. It's not basically somewhere on your local machine. You see on the right-hand side, Spark has 3 executors and basically then 4 cores. So it really distributes the job. Now for a very simple one, you see there's not many tasks. There's not much to cut from one source code line. If you think about how Spark works, this is underneath idea of breaking it into parallel pieces, there's not much to parallelize. right? And now when I executed it further, you see for the next cell, again, execution was taken. Essentially what we here did is just, if you remember, now taking those interesting parts out of the data, which are for us quite interesting. So kind of the ID of the restaurant, the name of the restaurant, the results, so pass, fail, etc. And of course, the violations would be very interesting for us because they reflect largely the features. So, and when you execute this again, you know, what we do here in the end is just one task. It's not much to do. It takes 2 seconds. Of course, take away the message if you have a large machine learning problem, more data, big data to prepare. Then it could be even that this whole data cannot be in your laptop anymore, you know, loaded. It will be crashing. So for this here, you have a scalability. This is almost endless given your 3 executors, right? So here you can, of course, scale as much as you configured. There are also options that you extend this in a more variable fashion. But you see here, there's of course no need. But of course, the same way you would execute it, you would not see it. The only thing you would see is that Spark maybe has here 25 executors and many more cores. So this is a very beautiful way of saying underneath we have lots of Spark workers, lots of Spark executors that benefit from this in memory, while I'm just, you know, relaxed and play around here in this Jupyter notebook with a couple of Python lines. And you see the result is then beautiful explained. And if we continue this, we want basically a little bit to analyze now the result and the distinct feature of it, which is interesting because now we want to really understand where are all the different ones, the counts from all of these different. And you can imagine, so we had lots of samples, if you remember one of the earlier lectures. So this is not something where you immediately could go through all of this. It's in the thousands. And this shows you a little bit like that there needs to be different tasks doing it, right? And there are different tasks executed for it. And of course, some of them are overlapping and basically still in running while I already contributed, or basically with the next column. Here you need to be careful. Basically, sometimes you should be waiting until completed. I was a bit more going forward to really understand if the script has errors or so. But it worked nicely, and it should also in your assignment. But you see here also that depending on what exact now execution you have on things you do, you really have to think about what's happening really. And you see here, firstly, we work on all the samples. We want to have those which are distinct in the results. So this is much more different than showing the top 5 rows. It's different than selecting complete columns because essentially that's just a data structure. Here I analyze the data and see which of those are distinct from each other. To understand this, what I had also on the slides, that there actually are 5 classes, not 2. And you know, then we did the count, we see the pass and so on. And you can see there the same results, just in a different order of fashion. Also shedding light that this maybe was parallelized differently to give you essentially the counting here. And here's now the visualization that we had that you can maybe put in an infographic or not. We set pass as a majority, fail is just, a smaller fraction, and then we had the other ones from the classes. So let's work and do some data preparation on it in order to really, get to the more interesting things, which are machine learning and pipelines. And that's what I wanted to take basically now a shot. But before we go there, let us come back a little bit now on these aspects of the training data and things I have a little bit again on a theoretical slide. So here it's important really to understand now we have 2 processes. And if you are essentially in a really practical setup and a machine learning expert, then you have even much more. You have training, validation, and testing, so to speak. But let's keep it simple here in the non-machine learning course really. Where we have training and testing, right? Or basically it's machine learning still, of course, but and you learn here the basics. But if you want to be really an expert in machine learning, you have to go to more courses showing you also validation for model selection, regularization, and things like that. We don't work here. It's inherent a little bit. But it shows you nicely now what this training process is. And that is one of the learning experience. But You see it is related, of course, to the data. So we start here with a tokenizer. We said these are all words, the violations we want to put in some form of a, feature vector. And this is nicely done with this hashing and so on. So it's still not really, you would say, modeling, it's more feature preparation. Now, the beauty of these pipelines is now in Apache Spark and in data science in general, that you include this in your analysis steps, because for the training process and for the testing process, you need both. You see that on the upper hand, you see the training process, and we come down there to the testing process later. So for the training process, to the tokenizer, we have this raw text of the violations. We go and put it to words. The words then are put into feature vectors to really learn something more in a mathematical fashion for the logistic function and for the logistic regression. Now, and what's not now happening is not that there is this magic algorithm like a perceptron learning algorithm anymore, right? Instead, we try to fit the data. We fit the data on the samples that we have from the training set that we read. So that means we have always a Y that, is guiding basically the output and say which class it is. We have all the feature vectors, but we have to transform it every time before. So this pipeline ensures that it's the same way transformed for this logistic regression. Once this is activated, we basically do an iterative learning, again and again, iteration, and pick, and actually check the misclassifications and see we have still some error. And the error function is loaded. I will talk about it in a minute. But essentially what we're saying is we're kind of going downhill a so-called error function that is still not defined here. I come to that in a moment. But we try to reduce the error. That is a learning process. That's why it's also an optimization problem. You minimize the error, essentially. And with this, we basically have a tool set from the larger mathematics community, from the larger optimization community, where we just borrow essentially stochastic gradient descent from and say we always go the steepest descent, so to speak, to the error in order to more quicker arrive to a solution. This is loaded. We talk in lecture 6 and lecture 7 a little bit more about it when we talk about deep neural networks and traps in neural networks, having local minima and so forth. But for the simple start here of the lecture series, we assume a little bit a very optimistic situation here where we said we can go downhill and we'll find also the global optimum, so to speak, in order to push the error down. So, and this would be the learning, right? So learning is really optimizing this function which lives essentially in the memory. And the point is now, once these iterations have been converged, the error is to the minimum, then we have this logistic regression model, the thing that you see here out of blue. So what you can see is out of the training process should be, in a way, always a model coming out. Could be a neural network model with concrete weights, could be logistic regression model with concrete weights, could be a support vector machine with having identified the clear support vectors that span the optimal line between the samples. Whatever it is in the training process, you need training data, but the end of the results is a model. Of course, putting this to disk is sometimes beneficial, especially if you think about deep neural networks, lots of weights that have been trained and were costly to train it. So you don't want to lose it having just in memory. But here we keep it in memory to also, of course, benefit from Spark's fast analysis. So having done this, we have to talk a little bit about transformers, estimators in this process. Which is essentially saying that we have a couple of different areas here. This is an estimator when we talk about that we have a fit function. Estimator because it predicts something, not really yet, it creates something. It estimates what should be coming out, and by this creating a model for this. So it fits the data, and we come later then to transformers, which we then use in a testing phase where the whole pipeline model that we just in blue have dropped essentially are transformers, again, including all the data. But this is something we will allude to again and again, right? Interesting is just that the existing pipeline model now, the logistic regression model we have in the memory, we can reuse it and will be used for testing later. Now, let's looking at it and by way also recap what we said about the training examples. What is now this learning? What are these iterations? So we had the last time this loss function defined, which is a bit something you can define. It is often with a logistic function that, of course, the loss function is a logistic loss, which is there defined, but does not need to be. So the error function can be defined. You put the training samples in, and because you have always this y, you can always, the kind of label that was originally thought about it, that makes it supervised learning. You can always compare, is it better or worse than before? Of course, now putting it always through the logistic function, seeing if the result is 0 or 1. So if it's not like this, you will see that with many samples, it will go again and go again and go again, and will basically change the weights all the time. And by adjusting the weights using the stochastic gradient descent optimization algorithm, over time iteratively comes to a better solution. And this is exactly what essentially this learning means, right? Reducing the error, and you would always go iteratively and changing then towards a new position which is lower, and then you go up downhill in order to minimize the error. This means also usually in application problems there will be not 0 error, right? So you have to define some iterations. And if you think about how we initialize this, we had here max iteration 10. So this was one parameter. And actually this is a regularization parameter for those of you who are a little bit know already in machine learning. This is very important for generalization of machine learning models, but it's a more advanced topic. I don't want to talk in this lecture because it would overload the people. We talk a bit again in lecture 6 and lecture 7 when we talk about deep learning networks. They have also regularization. Neural networks have regularization. It's the same idea essentially on this. Right, having talked about this and connected this, it go iteratively. Again, iteration by iteration, iteration will knock down the error, so to speak, and this is the learning. In this cluster, we have done so. We have basically had the fit here in this data. So when we think about this, we can always go back to to this Jupyter that we had here. We basically have prepared the data. You see here with the number of predictions and so on. Oh, wait a second, it's a little bit up. Here's the tokenizer. We had here the max iteration 10, and then the parameter, and you see nicely also how many jobs, of course, are needed now. Because what's coming out here in this model is now this transformer, which includes the whole pipeline. It is a logistic regression model as pipeline to also include, of course, the tokenizer, the word vector. Because if you have new data, new testing data, you again have to push through it, the tokenizer, the word vector. The only thing in testing is you don't train anything. You just reuse the model. But in order to train the model, you need lots of iteration, optimization. And this, of course, is actually, in many cases, the most computing task aspect of it. Now in our, let's say, toy problem or demo problem here, this is, of course, quick executed. Still, you see there's a potentially lots of executions that you could do, especially if you would have more Spark executors. But you never specified really how many are parallelized. So the machinery will actually do this depending on the data structure, on the algorithm you pick, the pipelines, the stages on its own. So this is a quite neat functionality. You can configure, of course, if you like, but usually you basically have the benefit that lots of these is abstracted from you away. And that is, of course, one of the design ideas of Apache Spark. Now, having said this, we have now trained this model and we want to do something with it. So let's go a little bit back to the slides and formalize what we found here. So we said we had a hypothesis, and this was the solution tools we have only together with a learning algorithm. So you will find artificial neural networks, they have back propagation. You have support vector machines, they have quadratic programming. You have logistic regression, it has an SGD or any other optimization algorithm that fits. So you would see a really solution tool that connects now the input from the training examples to get us to some final hypothesis, which was more or less the output of the function we want to have that shows that it's approximating the initial function we will never know, but it's in line with all the training examples, or let's say with many of them. But how many of them is an error? and an error measure we don't have modeled yet, so we have to come to this. In our learning example, this was clear. We had the hypothesis set was perceptron model, and our learning algorithm was a perceptron learning algorithm. That was our flower example, right? We had in lecture 2. Now lecture 3 was more elaborate, so you would say here we have the hypothesis set in lecture 3, which was now logistic regression. The learning algorithm that goes with it essentially was the optimization we found together with the error measure that will come in a moment, which then brings you kind of the optimization to come from the training example to the final hypothesis. And no matter what supervised learning algorithm you take, it will go along the same structure that you see here. Now, what is, let's say, again, an example for it? We had one in lecture 2 again, perceptron learning algorithm and perceptron model. Now you have basically this W's trained. You go iteratively, you have changed the weight, changed the weight, changed the weight, and suddenly Y is just in line with most of the data. Of course, in the perceptron learning algorithm, that means all the data because it needs to be linearly separable. But in our case, when we go to the logistic regression, that's not the case. So how we model this? So there's another notion in machine learning which is important I kept from you so far. And you see that by picking it in Spark, it's automatically inherently defined as an error measure. Error measure is how you can see a normal exam or a quiz that's maybe about to come later. It means we have to measure how good we are. So how is the, let's say, step we take from this optimization better than before? That means there needs to be some error measure, and this error measure is usually an error function, a loss function that shows a little bit, you know, how we perform in learning. And the goal is usually to get this really down. And by doing so, you're changing in this logistic regression setup now really this red entities, this W's, that you put then into the sigmoid function, into the logistic function. But with this automatically changing the weights all the time, you also change the nature of the hypothesis. If you want, because it's a linear learning model, still putting it through a non-linearity, but still you would change the line in a sense, right? By changing the weights as we learned. So when you do this, of course, there the point is that it is another hypothesis. Anytime you change this, you basically have automatically also another hypothesis, because it's not only the type of neural network of support vector machine, it's also the parameters or the coefficients, the trained ones, that define then this hypothesis. So when we pick this, now put that into the game and add the error measure, and now you have an almost complete way how machine learning works in a basically supervised fashion. There's something what is called a probability distribution, which means you assume the same probability distribution goes alongside it. What does that mean? That means if you do, movie recommendations and learn from samples, for instance, you don't want to mix necessarily Netflix with another streaming service because it has maybe other, probability distribution that gave rise to the training samples. Other features and so on. And it has a little bit to do with statistical learning theory on which machine learning is built on. Because essentially machine learning, unfortunately, is not possible because, we have sometimes a very unideal situation that the same X in, the same X vector in gives different Ys. And that's not a mathematical function, that's not deterministic. So what machine learning has as trick, using statistical learning theory, which was then the breakthrough of a so-called PAAS learning, probabilistic approximately correct learning, is then that you have basically essentially a target distribution plus noise you kind of get to. And you assume, and this is the only assumption, you don't assume a normal distribution, a heavyweight, whatever distribution, you don't care which one. You just say it should be the same. You basically try to learn from and then have the results back from when you think about the test set, for instance. So this is already alluding to more complexities in machine learning. Usually you would go to things like Vapnik-Chervonenkis, dimensions, capacities of models. How could we learn? Why can we learn? But this is all elements which, other people at the University of Iceland teach right now. Stein, for instance, or Hafstein and others. And of course, you can always come to me and ask about these things. I teach it also in many occasions, but in this course, we keep it more simpler, and now would say that's enough what we have for machine learning theory. But again, if you really want to have a job in this area, I encourage you to look more into statistical learning theory. Good sources for this are, for instance, also my teaching slides that you find from other occasions when you look on my website, morrisriedel.de, and then /teaching, you'll see also 3 days tutorials just on deep learning, 3 days tutorial just on machine learning, including statistical learning theory, the law of large numbers, Watnik-Chervonenkis inequalities, Watnik-Chervonenkis dimension, things about capacities of models, lots of elements which are very important to understand in practice in machine learning, but it's just too much to actually have this in this course as well. So let's go back a little bit before we close this practical lecture part. When we think about the test set now we think about the pipeline are very neat. They're very good because essentially we can now read any other data set, which is here. So you see food inspections 2, another file is read. Basically where you then have again a little bit of sampling, right? You say again, we want just results with fail or pass with conditions. But I give it the same way into this model. This model is already existing. That was this pipeline model. And now I use the idea that you had in this graphic of saying we transform it along the way, tokenizer, workers, and then put it to the predictions. The point is now that, of course, there is nothing happening from the training perspective, right? You see that very nicely in this slide. So this part means we reuse the model that we created on top. But of course, in order to reuse it, we cannot just throw every data to it. So we use a pipeline concept here of saying it goes with the data flow, basically. And if you throw now the raw text from the test set in, you have to tokenize and hashing and have the feature vectors in order to use the model, but we don't train it anymore. There are no iterations. And usually you would say this then should be relatively fast. It also is very scalable because in a way the nature is very, let's say, independent from each other. You can really nicely parallelize this and scale out to the whole cluster. And this is very beautiful now, not only in the pipeline concept, it really ensures as a key benefit, and this might be an exam question actually, the key benefit is really that you include in this pipelines really also the thinking of the identical feature pre-processing, the feature processings, all the steps necessary to use a model, right? And this is an important part because there's lots of flexibility in these models in order to be used. Now, I think for the evaluation, we have said a lot. You have tried it out already. Remember in this chart here, when you do it, that it's a bit misleading, the example, because here is a positive is a negative result, so to speak, right? The positive means it's a failed food inspection, just because, of course, it's not the wording positive, it's just that the model is positive about being failed. So this is, of course, something where you have to twist your mind to the -1, so to speak. But I think having these examples, you can quickly do this. Just let me point out at the end of the lecture here today that, of course, now the MLlib of Spark, we have now looked just in logistic regression to a very good detail. Of course, there are many other algorithms, and in lecture 11, we will review a couple of those, not necessarily in MS Azure. You will see K-means is in MS Azure, but you see on the right-hand side, for instance, to use collaborative filtering, another technique that is also available in the MLlib in Spark, but you can also use it then maybe not in MS Azure, but in another cloud, which is a Google Collaboratory, right? So, and from this, you have something like movie rentals. You have different customers, let's say from Netflix, and you have different movies, and they have let's say a legend about 1 to 5 of ratings. When you have done this, you end up with a matrix that you see here, right? You can see basically each customer gave this movie so and so much of a rating. Now, what you're interested in is not essentially only saying, what are the movies, others have looked and I should look in general. It's more interesting that other users that are so similar like me have looked. That makes it a personalized recommender system, right? Collaborative filtering systems, which really take also the others, not in terms of a general assumption from the data, but also which are the users which are most similar to me and then recommend the movies to me. And you can do this with a recommendation engine, but again, it would be too much in this lecture to just go for it. But essentially, if you want to try it, there's an Python notebook in the Google Collaboratory, and we will come to this actually more in a couple of lectures now, because we really have in the next lectures really more about clouds again, data structures. We have done a lot. Now we have to do the bigger picture, data centers design, larger, how actually clouds scale with the demand. So that's really all I wanted to leave on the label here for you. So you have now, with this kind of cheat, if you want, this overview about machine learning blocks, building blocks really, a good blueprint how to do machine learning. It's still not enough. Statistical learning theory is there for the rescue for you to learn it. But then the different models will be playing a very similar way. You pick another optimization algorithm, you pick maybe other features, but you still have basically the hypothesis, you have a model, and then you basically, with the model goes a training algorithm, which could be backpropagation maybe for neural networks, for instance, or quadratic programming for support vector machines. Whatever you pick, there would be this kind of certain structure, and you always would have some error that you need to knock down in order to learn. Right, so that's all for this lecture. Basically,